So, yesterday we looked at what is a semiconductor and we derived some expressions for the number of electrons in the conduction band, in the valence band, the intrinsic charge carriers, and so on. The type of semiconductors we looked at yesterday were intrinsic semiconductors. Intrinsic meaning pure. So, we are not adding any sort of impurity or any other material to the semiconductor. So whatever conduction is happening only because of the electron hole pairs belonging to that material itself. That's what we looked at yesterday. So in today's and tomorrow's classes we are going to be looking at extrinsic semiconductors, where you have a semiconductor element already, and then you add another element to it. You add atoms of another element, and those extra electrons also contribute to the conduction. So within extrinsic we have two types, N type and P type. Today we'll be looking at N type and tomorrow we'll look at P type. So what are N type semiconductors? First of all, in an N type semiconductor, the pentavalent impurity replaces the covalently bonded host atoms. So when we were looking at intrinsic semiconductors, I gave the example of silicon, and I said silicon has 4 electrons in its outermost orbit. It needs 4 more to complete the 8 electrons. So that is an example of a tetravalent element because it has 4 electrons in the outermost orbit. Now in an N-type semiconductor, again the semiconductor itself is a tetravalent element. It is silicon or some such element. But to it, the impurity you are adding is a pentavalent element, meaning an element whose outermost orbit contains 5 electrons. For example, phosphorus. So this is the normal atomic structure of, let's say, silicon. There are 4 electrons in the outermost orbit of each atom, and then I am replacing one atom of silicon with an atom of phosphorus, which has 5 electrons. So this last electron is not involved in any covalent bond. It is loosely bound to its nucleus with a small binding energy. So when I replace this silicon atom with phosphorus or some pentavalent atom, again the surrounding silicon atoms, they only need 4 atoms to complete their covalent bond. So 4 out of these 5 phosphorus electrons will enter into covalent bonds with the neighboring silicon atoms. But the one last electron, which is not a part of any covalent bond, it will just remain in that orbit, but it is not held together with the nucleus by a very strong binding force. Its binding energy is very small. It is of the order 0.045 electron volts. Meaning if I supply a small amount of energy itself, that electron will become free. It will break free from this atom and go into the conduction band. So when that happens, what we get is one free electron in the conduction band and one positive charge, unit positive charge on this atom, but a hole is not created. So this is an important point which we need to understand. In an intrinsic semiconductor, when you apply energy, the electron gets excited, it moves into the conduction band, creating creating a corresponding hole in the valence band. But in an N-type extrinsic semiconductor, because you are introducing an element which has one extra electron, when you supply a small amount of energy, that extra electron gets excited, it moves into the conduction band, and because this pentavalent atom is losing one electron, it gains one unit positive charge, but a hole is not created. So that is the basic electron movement without generation of holes in the valence band. This pentavalent impurity which donates electrons is called a donor. The ionization energy is 1/25 of the energy gap, and since the donated electron occupies the conduction band, it implies that the energy is closer to EC. So what this point means is, I have a free electron here. I provide 0.045 electron volts of energy to it. This electron goes into the conduction band, meaning the average energy level of these electrons should have been close to the conduction band, and the difference between them is 0.045 electron volts. That is what this point says. So because we're talking about donor atoms or donor electrons, we consider the average energy level of these electrons as ED, where D stands for donor. And what this point tells us is ED lies closer to EC than EV, and the distance between ED and EC is 0.045 electron volts. So that is an introduction to N-type semiconductors.